Hello, my name is Michael Kaler, and I am the lab manager of the Diffraction facility, which is a user facility located at the University of Tennessee, Knoxville. In this video, I will show you how to take a list of peak locations and determine which H, K, and L values correspond to them. In other words, which atomic plane created each of the peaks. I will also show you how to calculate the lattice parameter. All of this is assuming that you have a cubic structure, though. If you have a structure from some other crystal system, some of these details would change. You will notice that I have a lot of information down here. Some of this, namely the tables, contains information that I find helpful to keep in my Excel file as I perform the indexing. Anything in the blue boxes is just an equation, and those you don't need to worry about having in your Excel file. I'm just using these to help explain the calculations that I'm performing. Let's start out assuming that we have copper K-alpha radiation, so our wavelength will be about 1.5406 angstroms. Here are some 2 theta peak locations for a sample. I want to identify which atomic plane corresponds to each peak, and I want to calculate the lattice parameter. The first thing that I will calculate is theta, and I want that in radians. That is simply going to equal radians of this value divided by 2. I'll hit enter. If I click that cell and double click this, it copies it down. Next, we will calculate the d-spacing of each of these reflections. I'll just copy that, paste it down there. In order to calculate the d-spacing, all you need to do is take Bragg's law and rearrange to solve for d. So we see what the equation is here. That will equal our wavelength divided by 2 times sine of our theta value in radians. When I copy this down, each of these numbers will increase by 1 every time I move down a row. That's what I want to happen with this C5 because I have a different theta value for each reflection, but I always want to use the same wavelength. So to prevent that 2 from changing, I will put a $sign next to it. I'll hit enter and then copy that down. Next, we want to calculate 1 over d squared. I'll highlight this, right-click, format cells, and check superscript just to make it look nicer. This is going to simply equal 1 over our d-spacing squared. And I will copy that down. We now want to start taking ratios of these values. So I will set up a few different columns: ratio, ratio times 2, ratio times 3, and then m, which I will explain in a moment. For ratio, that is going to equal this value divided by this value. For the numerator, I want that to change every time I go down a row, but for the denominator, I always want it to remain this value here. As such, I will put my $sign there, and then copy it down. This will simply equal 2 times my ratio, and this equals 3 times my ratio. I can highlight this and copy it down. Just to make this a little bit easier to read, I'll highlight all of these cells here, right-click, format cells, come over here to number, make it a number, and give it 2 decimal places. Okay. What we are trying to do here is find the ratio that will give us good values for m. M is calculated, as you can see here or down here, by h squared plus k squared plus l squared. This helps us determine which planes correspond to each reflection. We see that we must have whole numbers for our HKL values. If we had an HKL of 100, that would give us an M value of 1. An HKL of 111 would give us an M value of 3. In this regard, we need to find a ratio that gives us only whole numbers. We see that for these first two columns, they give us very large decimals, but the third column gives us whole numbers. I will point out that if you had something like 19.01 or 19.02, something like that, it is still very, very close to 19, so I would say that is good enough. You don't have to be perfectly on 19, but you don't want any large deviations from a whole number. So we are happy now that we have whole numbers, but we need to keep an eye out for forbidden reflections. These correspond to values of M that simply don't exist for any crystal structure, not just cubic. I should mention the fact that each type of structure also has its own additional forbidden reflections, but I will get to those in a moment. The forbidden reflections for all structures exist because there are no combinations of whole numbers for H, K, and L that will give us these values of M. You can see here for, say, 7, if we come over here to this table, we see that 6 corresponds to a 211 plane, 8 corresponds to a 220 plane, but there is nothing in between, no combination of numbers that can give us 7. I have listed the first 4 forbidden numbers, but the ellipses implies that there are others higher than 28, but I will leave determining those to you. If we see whole numbers here, that's a first check to make sure that we have a good ratio column. We also want to make sure that none of these numbers correspond to forbidden reflections. We are looking good there too, so I will take that and copy it over here. I guess you don't really need this step, but I like to do this so that my good column is separated out from my ratio columns to more easily focus on the good values. I will also point out that just based off of this column alone, we can now determine what kind of cubic structure we have. These are the allowed reflections for the different types of cubic structures. We see that if we have a simple cubic structure, we can have any value of M other than these forbidden values. So if we had a simple cubic system, this first one would be 1, then 2, 3, 4, 5. You do want to make sure that if you think you have a simple cubic structure, you want to use diffraction peaks that will get you to at least an M value of 8 so that you can make sure that 7 doesn't appear. If you did see a 7, it would tell you that ratio column is wrong and you would need to continue looking for a good column. BCC can have even values for M. FCC and FCC diamond give you the values shown here. Again, the ellipses simply means that there are more values that are acceptable. I will leave a link in the description below that shows you the rules for allowable and forbidden reflections for each type of crystal structure. You can use those to determine more of these values if needed. Getting back to the table up here, I see that these are my M values, so I can use those to determine my HKL values for each reflection. I see a value of 3 for M corresponds to a 111 plane. 8 corresponds to a 220 plane. 11 is 311. 16 is 400. And 19 is 331. That's why I like to keep this table down here so that I can very easily refer back to it to get these values. Once we have our HKL values, we can then determine our lattice parameter. I'll take this, copy it, and paste it over here because we will be working in angstroms. For cubic systems, we have this as our relationship between our d-spacing, HKL values, and our lattice parameter. If we rearrange this equation and solve for A, we get this equation. Thankfully, we have all of those variables already. We will say that A equals our d-spacing there times the square root of h squared plus k squared plus, well, I can't click it, but I can do left on the keyboard. Let me go back and put in a parenthesis, squared. That is what we get, and I will now copy that down. I'll probably just format these cells and choose a number that has 3 decimal places. I see that my lattice parameter is very consistent for all my reflections. That's a very good sign. If we had large differences, that would imply that we made a mistake somewhere, such as a mistake in an equation, or we have the wrong m values. I wouldn't worry overly if your last decimal place changed a little bit. That's still going to be very consistent. In that case, you could try taking the average of these values to get an estimate of your lattice parameter. In this case, though, the results are very consistent at 5.431. I will point out that these peak positions correspond to a silicon sample which has a lattice parameter of 5.431 angstroms, so this process was very accurate. And that is how you go through and determine the HKL values of each diffraction peak and determine the lattice parameter, assuming that you have a cubic crystal structure. If you have any questions, please leave them in the comment section below. Otherwise, Benjamin and I thank you for watching, and we hope you have a great day.